All right, we'll go ahead and get started. So today we're going to be talking about not a data structure. Once again, kind of branching off into some separate areas. And this is something that I think is really cool, and a lot of times people don't really learn about it. But it's a pretty simple conceptual model of programming. So the thing, it's called the Lambda Calculus, and don't be afraid of the name calculus. It's not like the calculus that you may have learned in school. It's nothing like that. It's not that complicated. It's just a set of a few very specific primitives and how they interact. And it's a pretty interesting way to look at kind of the basic ideas of programming. It was invented by Alonzo Church a very long time ago. I don't know the exact date. And this was before Alan Turing, I believe. So a lot of people consider the Lambda calculus to be the quote-unquote world's first functional programming language, and I will show you why. So let's go ahead and get started. I'm going to give you like the formal definition first, and then I'll explain it. So the formal definition is the Lambda calculus can be, it's basically, you have a term in the language, which is basically a statement. So your Lambda terms can either be variables, which are basically what they sound like. They're just values that vary. Lambda abstractions, and a lambda abstraction is defined by this rule. If t is a term, then lambda x dot t is a lambda term, and we'll explain what that means in a minute. And applications, and you can think of this as like a function application. If t and s are terms in the lambda calculus, then ts is a lambda term. And so that's all very vague and abstract. Let's bring it back to something that, well, let's look at the next slide. So slow down. That's a little bit too much to take in probably immediately, so let's slow down a little bit. So in layman's terms, the lambda calculus, again, you just have either variables. You've got the lambda abstraction is actually just a function. So these are anonymous functions. Sometimes they're called lambdas in programming languages that we know and love. Closures is another name for them. Basically, what a lambda abstraction is, sorry, this little backslash is supposed to be a lambda. The lambda, the beginning part of it that starts with the lambda, and then the variable name, the lambda x in this expression is like the arguments for the function. The dot is kind of the separator, and then everything that comes after it is like what you do with those arguments, so like the function body. So this function this lambda abstraction, it defines a function that takes a value x and simply returns x. And the third thing is lambda what did I call them? Sorry, lambda applications. Yeah, are functions in the lambda calculus applied to values. So, and that's a very specific. It's a very specific way of looking at it. It's much more general than that. But in this case, so we've got two lambda terms here. We've got the lambda x dot x that we just talked about, and this 5. And 5 is also a term. You know, it's a variable in the lambda calculus, so we can use it. And we can apply these things. We can apply the first term, the lambda x dot x, to the second term, 5, to get a value. And I'm not really going to talk about how the lambda calculus actually produces a value, but you can kind of look at it and understand, like, okay, this is a function that we're talking about, the lambda x dot x, and it's applied to the value 5. So kind of just plug in 5 for x, and you get 5. And that's called an application in the lambda calculus. Bringing it back to something that maybe we all understand, I think most programmers nowadays have at least some experience using JavaScript. So I kind of want to talk about the lambda calculus in terms of JavaScript, just so that, like, the syntax doesn't get in the way of understanding. This actually probably shouldn't be here. I think variables in the lambda calculus they're not necessarily. So the problem with the var is that it defines, like, this kind of globally scoped thing, or a scoped thing in general. And in the lambda calculus, you can't really do that. You're not going to follow, like, a sequential pattern. So saying var x really doesn't have any meaning at all. But what it would be is just like a value in your program. So if you wanted to apply x, if you wanted to apply a variable to a function, or apply a function to a variable, I'm sorry, that variable is still like you can think of that as a variable in the lambda calculus. The second thing, the lambda application, the lambda abstraction looks like this. Function that takes x and returns x. This is a valid JavaScript. It's a valid function definition. And so moving down, if we wanted to apply this to the value 5 like we did before, in JavaScript we can just wrap it in. We can wrap it in parentheses and apply it to a value. And this will produce 5 as it should. It's going to feed that 5 into the function and return it. So I just wanted to kind of take a quick detour here and talk about, like, how this looks in other languages, so that you can kind of understand the feeling of, like, a functional programming language, and understand, like, why, like, where it came from. So this is Common Lisp. Well, first off, we're going to look at this expression here in the lambda calculus. Lambda x, lambda y, x times y plus 1. So this is a function that takes x and y, multiplies x by y, and adds 1. Common Lisp was invented in 1981, and they use S expressions. So the operators come before the arguments to the operation. So, like, plus is a function that takes 2 values and produces a third. You just put the plus beforehand, kind of like reverse Polish notation, if you're familiar with that. But the key point is that Common Lisp obviously got the idea of how they wanted to do this from the lambda calculus, because they literally named their anonymous functions lambdas. Haskell came out in 1991. Haskell looks a lot like the lambda calculus as well. They let you kind of remove nested lambdas, but internally it still works the same way. So here, like if you squint at that, literally looks like the lambda calculus expression above. You have the backslash, which is supposed to look like a lambda if you look at it weird, and the arrow instead of the dot, but otherwise it looks exactly the same. ES6, which they just, they're in the process of moving into browsers and whatnot, and a lot of people are using through things like Babel. They just came out with this new syntax for JavaScript functions that looks a lot like the Lambda Calculus, and that happened 2015, 2016. I don't know when it's going to be implemented in browsers, but you get the idea. So these things are sort of ubiquitous. They pop up everywhere, and it all traces back to the Lambda Calculus, which was invented in the 30s or 40s, which is kind of cool. One thing that I want to mention before we move on to the next slide is that in the Lambda Calculus, when you apply a function, a function to a value, you can do it one by one. So we could apply this this expression to a single value. Say we wanted to apply it to the value 5. We could plug in 5 for x, but keep that second lambda term in the argument list, that y, and we would have a new function that takes another value and multiplies 5 times it plus 1. This is very cool. It's something that just kind of gets built out of the Lambda Calculus, and it's something that you don't see a whole lot in like mainstream programming languages, but you can do it in JavaScript, and you can do it in a bunch of functional programming languages. It's called partial application of functions. It's just kind of built out of the Lambda Calculus. Here's like another simple example of something that we can do. So one big thing in functional programming is that you should be able to take a function and apply it to, you should be able to use a function as like an argument to another function. And so that's what we can do here. If we choose some special, we choose names that kind of match up to what we're trying to do for our Lambda variables. Basically, we've got a function here that takes an f and it takes an x and it applies f to x. So let's imagine that f is a function that adds 1 to a value. We can plug in that addition function as the f, and then we can finally, after that, we can plug in 100. And when we evaluate this, we're going to be applying the lambda x plus 1 to the 100, and we're going to get 101 out. So this is kind of the way that this is how you can kind of build up. Well, it's very general. Like you can very easily see how you can build functions that take functions as arguments and apply them to other values. Some more examples. I'm just going to walk through like a few little examples of the Lambda Calculus because I think that it's pretty cool. You can do a lot with this stuff. Just even like the Lambda Calculus, the basic Lambda Calculus, you can actually do quite a bit with if you mess around with it. It's a very fun thing to kind of toy around with. So this is a function that takes, in the last slide we looked at a function that took a function and applied it to one argument. You can easily extend that and say, I want to take a function and 2 arguments and apply that function to both. So you can imagine f could be something like add, and add takes 2 numbers and adds them together. You could plug in that function and have a new function that adds that adds 2 numbers together. If that makes sense. Basically, it's just a way to apply a binary function to 2 arguments instead of applying a unary function to 1. And you can extend that out however far you want to go. Another thing that is really interesting is you can flip the arguments of a binary function. So this looks very similar The only difference is that we're taking the function and 2 arguments, and then we're applying them backwards. So you can imagine if you had something like append, which is order dependent. If you append A to B, you get AB. But if you append B to A, you get BA. And so if you applied this function to the append function, you'd have a new function which takes the second argument and puts it before the second. It takes the second argument and puts it before the first argument, which is kind of interesting. And there are a lot of different uses for that. Another thing that's actually kind of catching on these days is the composition of functions. This is something that happens in math, and it has for a long time. But in programming, it's very useful to say, I have 2 functions and I want to compose them. That is, I want to apply one function to an argument and then apply a second one to the result of that. With this lambda term, this gives you a generic function composition function that takes 2 functions, composes them, and gives you a new function that, given an x, applies that composed function to x. And just the last thing here, this function is something that takes, so we commonly refer to this lambda x.x as ID. It's identity. It's the identity function. It basically takes a value and returns it. If you apply it to itself, you get ID again, which is interesting. But just kind of, I wanted this example in here just to kind of show that you can apply a function to a function and get a function out, and that's totally fine. So I mentioned that the Lambda Calculus is like the world's first functional programming language. So what does that mean? First off, like the first thing that people ask is like, there's this concept of Turing completeness, and it basically says you can compute whatever you want, right? It says you have like a model of computation, and it's the model of computation that we want to use. Both of these guys, Alonzo Church and Alan Turing, were working on models of computation at the same time. And Alan Turing came up with the idea of a Turing machine, and Alonzo Church came up with the idea of the Lambda calculus. And what's interesting is Turing machines sort of inspired a whole lot of programming languages over the years, and most of the ones that we use today are pretty heavily tied to that model of thinking. But Alonzo Church, his Lambda calculus has actually been shown to be like functionally equivalent. They can be interchanged. So basically the point is the Lambda calculus is a Turing complete language. It's very simple, and it's been basically utilized and extended to come up with a whole set of programming languages that are maybe a little bit less mainstream. But I would encourage anybody who's like interested in functional programming to just mess around with the Lambda calculus for a little while. There are some great resources. If you look up like alligators and Lambda calculus, there's like a fun game that you can play that will teach you the rules of evaluation for the Lambda calculus. If you look up, you can look up the SKI combinators. Those are really interesting. You can build a lot of interesting functionality just by using those. And if you want, and just like a fun tidbit, if you're familiar with like Hacker News and the Y Combinator is actually a reference to the Lambda calculus, and it's very interesting. If you dig into the Lambda calculus, definitely check that out and see what the what the deal is. Thank you. Thanks for coming out, and I will see you next time.